In this video, I want to review everything that we know about the polynomial interpolation problem so far. The premise is that we're given a data set of n plus 1 data points on the graph of a function f, all distinct x values. We have determined that there's exactly one polynomial p of x, so that the degree of p of x is no more than n, and p evaluated at one of the x values from the data set gives the function value that corresponds to that x from the data set. We call this p of x the interpolating polynomial of smallest degree. In thinking about this interpolating polynomial, there's at least three completely different ways that I can think about this. Firstly, there's what you might think of as the usual way. You can write polynomials in the kind of format that you're used to from algebra and calculus. Then there's the Lagrange form, which for most of us is a new thing, which we previously talked about in class and will briefly go back over in a moment. And then there's what will eventually become the Newton form of the interpolating polynomial, which we'll talk about as well. As an example of this kind of thing, let's think about a data set that has three data points in it. One data point is 1, -2, another is 2, -1, and the third one is 5, 26. I want to think about trying to find the interpolating polynomial working directly with the kind of form that you would work with in college algebra. P of x equals ax squared plus bx plus c, and figure out what all is involved in approaching the problem in this way. Firstly, when x is equal to 1, the polynomial value needs to be -2 if it's to match the first data point. So -2 must be what I get when I calculate a times 1 squared plus b times 1 plus c. -1 needs to be what I get when x is 2. -1 needs to be a times 2 squared plus b times 2 plus c. And likewise, 26 needs to be what I get when I let the x equal 5. 26 needs to be a times 5 squared plus b times 5 plus c. We will rearrange these so that they look a little bit nicer. A plus b plus c needs to be -2. 4a plus 2b plus c needs to be -1, and 25a plus 5b plus c needs to be 26. We're led directly to a linear system of equations to solve if we want to do the interpolation problem in this way. If you look at that top equation, a plus b plus c equals -2 tells me that c is -2 minus a minus b. I'm going to substitute that into the other two equations. So 4a plus 2b plus c is -2 minus a minus b, has to be -1. And 25a plus 5b plus the c, which again is -2 minus a minus b, must end up giving me 26. These two equations only have two variables in them, so we'll continue this process after we clean the equations up a little. 3a plus b needs to be 1, and 24a plus 4b needs to be 28. Looking at the first equation, it's easy to solve it for b in terms of a. Substituting that into the second equation and doing college algebra on it eventually ends up telling me that the a has to be 2. The moment that I know that, though, b is 1 minus 3a, So I now know that b is -5, and since I have a formula for c in terms of a and b, it's easy by substituting in a equals 2 and b equal -5 to find out that the c is actually equal to 1. We now know all three of those coefficients. The polynomial is supposed to be p of x equals 2x squared minus 5x plus 1. We should probably check that in some way or the other. In order to check our work, we'll take x equal 1, x equal 2, and x equal 5, with a slight error on the x equal 5, put them into the alleged interpolating polynomial, and make sure that we get what we're supposed to. When x is 1, we get -2 for an answer, which is what we're supposed to get. When x is 2, we get -1 for an answer. And then, since apparently I hadn't had enough coffee when I wrote this, I accidentally stuck x equal 3 into the polynomial. 3 is not one of the x numbers out of my data set, so I was somewhat puzzled when I got that for an answer. 5, not 3. So I went off and calculated the polynomial evaluated at x equal 5, and I get the 26, as I am supposed to. The second of the ways that we're going to look at this sort of thing is called the Lagrange form. We introduced polynomials, which we call Ln, k of x. These are the products of x minus xi over xk minus xi, with the proviso we leave out the factor where I is k. We found out that there is a useful property of these things. If I take polynomial Ln, k and evaluate it at one of the x numbers from my data set, what I get back is the Kronecker delta. This is a quantity delta kj, which is equal to 1 if k and j are the same thing, and is equal to 0 if they're not. I'm going to build a polynomial, p of x, based on these Lagrange polynomials. P of x is going to be the sum k equals 0 to n of f of x number k times the Ln, k of x polynomial. Since each one of those polynomials is of degree n, when I multiply them by constants and add them up, the result is of degree at most n. If I evaluate polynomial p at x number j, what I end up with is the sum k equals 0 to n of f of xk delta kj. All of those terms are 0 except for one of them. When k is equal to j, though, I'll get f at xj, Kronecker delta jj, which is f at xj times 1, which is f at xj. Polynomial p has degree less than or equal to n and interpolates my data set. This is another way to write the interpolating polynomial down. To be a little bit more concrete, let's look at an example where n is 2. x0 will be 1, x1 will be 2, and x2 will be 5. For a given k index, there are three factors that you could use to build up the Lagrange polynomials: x minus x0 over xk minus x0, x minus x1 over xk minus x1, or x minus x2 over xk minus x2. For a given index k, you omit the factor that would cause division by 0, and putting in the values x0 equal 1, x1 equals 2, and x2 equal 5, we have the little factors that we will use to build the Lagrange polynomials. L2 comma 0 of x, the k is 0. The term that would cause division by 0 is the first one, so we leave it out. Then we simplify the algebra, and we have an expression for L2 comma 0 of x. L2 comma 1 of x is computed in the same sort of way. K is now 1, so the middle factor would have x1 minus x1 in the denominator, so it's that one that we leave out. L2 comma 1 of x is negative 1/3 x minus 1 x minus 5. And likewise, we can figure out that L2 comma 2 of x is 1/12 x minus 1 x minus 2. Now, if we take these Lagrange polynomials that we've figured out and write out the actual interpolating polynomial in Lagrange form, you see that it turns into this just horrific mess. It doesn't look anything like the other answer that we got. A person might be forgiven for thinking that this is a different polynomial, but we'll see about that. I've typed the polynomial that I got into my calculator, making no particular effort to simplify it. I'll draw the graph of it, and then I'm going to use the trace feature to see if the y-coordinates on the graph are what they're supposed to be. That one worked out all right. That one worked out all right. And that one worked out all right. The polynomial that we have computed using the Lagrange form interpolates the data set. Since we know from the theory there is only one polynomial of degree 2 or less that passes through 3 data points with distinct x values, the only conclusion that we can draw is, even though this last calculation that we did produced a polynomial that looks nothing like the others, in point of fact, it is the same polynomial. The third form of the interpolating polynomial that I want to think about is this form that, as I've alluded to, is eventually going to lead us to the Newton method. If you give me any polynomial of degree n or less and numbers x0, x1, x2 out to xn, then the polynomial can be written in the format constant plus constant times x minus x0 plus another constant times x minus x0, x minus x1, and so on and so forth. Since this can be done for any polynomial of degree n or less, in particular, it can be done for our interpolating polynomial. In particular, for n equal 2, the form of the polynomial we're now looking at is p of x equals b0 plus b1 x minus x0 plus b2 x minus x0 x minus x1. If I think of doing this with our specific x values, it seems strange that x2 equal 5 doesn't have any influence, no direct influence, but as it turns out, it'll have an indirect influence instead. When you evaluate the polynomial at x equal 1, the second and third terms are both 0. This immediately tells me that negative 2 and b0 are the same number, so when I write my polynomial down from now on, I'm just going to write in negative 2 for b0. When x is 2, I want the p of x to be negative 1 to match with my data set. This time only the last term is 0, but on the other hand, I have only one variable in this equation now, and it's easily seen that b1 has to equal 1. Even though there's no term with x minus 5 in it, The fact that the point 526 needs to be on the graph of the interpolating polynomial does figure into this. If I make x equal 5, I have to insist that p of x come up to be 26. Doing the arithmetic in algebra, it develops that b2 has to be equal to 2. I now know all of the coefficients in my third form of the interpolating polynomial. So p of x is negative 2 plus 1 times x minus 1 plus 2 times x minus 1 times x minus 2. Just as before, this appears to not look like the other form of the interpolating polynomial at all, but as we're about to see, in point of fact, it is the same. Multiply everything out using college algebra. When the dust finally settles, you find out that this polynomial is the same as 2x squared minus 5x plus 1, which is the same thing that we got from version 1, and we convinced ourselves that what we got from version 2 was the same as version 1. All three of these different formats for writing down the interpolating polynomial are in fact the same polynomial,